Good weekends, y'all? Yeah? Alright. Don't forget we are having our test coming up. And just speaking about your organic test, just want to tell you all that sometimes I get students and they think that they're not doing very well, but overall when they look at the program they are doing, they're doing okay. Like for example, this is kind of an extreme example, and I certainly don't want y'all to fall into this category. But one time I had a student, and that student took this course 3 times. And 2 of those times they made F's in the class, and then the last time they made a C in the class. And I certainly don't want that to be y'all, right? Because it's a lot of work and it's just not what I want for y'all. But this particular student went on in the chemistry program, did very well, and now they're working at some lab up near Baton Rouge and doing well, have a job that they really like. So sometimes you feel like you're just sort of behind in the program, but you're not really. You're moving on and you're moving forward. You wouldn't be here if you couldn't succeed in the chemistry program or the geomatics program or the biology program, but since most of you are chemists. So just sort of keep an eye on that overarching goal, even when you get a bad score in organic or in physics or whatever it is that you get a bad score in. That everybody makes bad grades. Well, some people don't, but like I made bad grades in college, right? Everybody, practically every normal person makes a bad grade in college. Like, not my wife, she made a 4.0 in the end, but but she's not normal, okay? And we're thankful for those people, but normal people mess up sometimes, and normal people have lives and they have other competing interests, and that's okay, all right? But I know that we're here to help you guys do as well as you can, and that's our job, is to help you succeed. So let us help you in the way that we can. We will have our test on Friday. It's gonna cover picking up with household circuits, right? RC circuits, and then the chapter 4, which is on current and power. So, oh no, I'm sorry. Let's see. I told y'all this before. Can y'all tell me? We're doing household circuits and RC circuits, and then the chapter on current. Do we have multi-loop circuits on this test? So y'all have already done that. Is that right? I'm getting y'all mixed up with my other class. What did we do on the last exam? We did multi-loop on the last exam? Let me check. What's that?
Chapter 3, 4, and sum of 5.
That's what we have, chapter 3, 4, and sum of 5, right? The chapter on current and power, so knowing the definition of current and power. Chapter 4, all of chapter 4, which includes multi-loop circuits and combination circuits. You'll see both of those, a multi-loop and a combination circuit. RC circuits, household circuits, and then a little bit of chapter 5, and I'll let you know at the end of class today. You're going to have to do a cross product, basically, and there are probably going to be 1 of 2 problems that you can have, but they work out practically the same. So let's wrap that up today, and then Wednesday we'll use completely for review, I think, and so we'll get prepared for that exam on Friday. Let's see, so we're dealing with magnetic fields. The SI unit for the magnetic field is the Tesla, like the car. But it's actually not named after the car. It's named after Nikola Tesla. You don't need to know that for the test, but it's just sort of interesting. And so when we abbreviate it as a capital T. Sometimes, and we're not going to use Gauss in this class, but sometimes other books might use Gauss as a measurement of magnetic fields. That's named after by the same scientist that developed Gauss's law. It was a person. And 1 Tesla is equal to what? 10,000 Gauss. All right. As I said, we're going to use the right-hand rule a bit, and you'll have some multiple choice answers on this test that deal with the right-hand rule, where I give you a velocity and or a magnetic field and or a force vector, and you have to tell me what the other is. And we've seen the right-hand rule, right? We did the I cross J equals K, and when we did that, this is I, J, K. When we did that, we said that our index finger goes in the direction of I, our middle finger goes in the direction of J, and then our thumb gives the direction K, which is the result of the cross product of I cross J. And so in a similar way, we're going to use the cross product to determine the direction of the force. Now remember, a force is equal to QV cross B. And so, for example, I'll do this first one, and then you can do the other two. First of all, when I look at one like this, I know that my vectors have to be orthogonal. That is, that they're all 90 degrees to one another. And so if I have a vector in the y direction and a vector in the x direction, then I know the answer has to be either plus or minus which direction? K direction or z direction, either into or out of the page. It has to be that because they're orthogonal to one another. And if they're orthogonal, then I take out the x direction, take out the y direction, so it has to be in either the plus or minus z direction. So here, I let my index finger go in the direction of v. My magnetic field vector, that's my middle finger, goes in the direction of b. And so my thumb gives the direction, that orthogonal vector, which is in the plus k direction. So I would draw that as a circle with a dot. I would write plus k, r, you might write plus z. Any one of those would be appropriate. All right, I want you to try these next two on your own. What is the direction here of the force vector? This is the force, I'm not sure if I said that. But what is the direction of the force vector for these other two scenarios where I give you v and v? We'll do it as clicker questions. And by the way, we know for this one that it's either in the plus or minus x direction. And for this one, it's either in the plus or minus what direction? The one on the far right. Right, in the I direction, or the plus or minus x. All right, we'll do the middle one first. Don't feel goofy to use your right hand, okay? That's sort of why we have it, is to use our right hand for the right hand rule. You can hold it up, show everybody if you want. All right, we're sort of split between A and B. So remember, our index finger goes in the direction of V, and then you need to orient your middle finger. It's either going to be like this or like this, so that it goes in the direction of B, and then your thumb will give the direction of V. On your test, it'll be a little easier because you'll be able to sort of rotate the paper around. Try this. It's in the homework, okay? Make sure that you can do this because it'll be worth, 5 to 7 points on your test. All right, let's stop at 128. Okay. All right. First time's a little hard. V is in this direction. B is into the page, so I have to do my finger so that it goes into the page. And then my thumb gives the direction of the force. That's what, to the right? So that's in the positive x direction. So A is the right answer. Let's try this next one, okay? All right, let's stop at 45, I think. Yeah, 45, just 10 more seconds. A little bit better on this one. 5 seconds. Oh, no, I'm sorry, not any better. Okay, so here, V is out of the page. So I need to have my index finger is in the direction of V. Our magnetic field is down, And so that means that our force is to the right? So that's the positive x direction. And I want to remind you that the reason that I limited these to plus and minus x is for this one, for example, I already had the y or the j direction. I already had the z direction here. So since they're orthogonal vectors, the other one has to lie along the x-axis or in the I direction. All right, so here is A. Let's do a few more on the concept test. You can turn to the back. What is the direction of the magnetic force for this particle? Here, I've drawn the magnetic field as a bunch of x's. That means that this positive particle is entering this region that has this magnetic field. We'll start to think about this when we look at mass spectrometers, because that's how they work. They send particles through a magnetic field and see how they respond. So what is the direction of the force here? First of all, try to imagine, what is it going to be, the I, J, or K directions? And then is it positive or negative of that? Okay, most of you have rightly determined that it has to be either what or what of these options. That it's going to be in the X, Y, or Z direction. X is right, because this is Z, this is Y, so it has to be either D or E. Most of you have already found that, a few of you have not. But that'll really help you if you can just sort of get rid of most of the options. And now it's a matter of, well, is it positive or negative? Is it to the right or is it to the left in the X direction? Let's stop it. Yeah, Brennan?
Can you hint me on which one you do first, which direction?
For the right-hand rule, you mean?
Yes.
Yep. So I have QV cross B. First, well, it's not really a matter of first. It's just getting your fingers in the right direction. I usually do V first. That's my index.
Okay.
B is my middle. F is my thumb. I would consider this cheating, but while you're doing your homework, you can write V, B, V, B, and F as you're going through homework if you want to do it. But don't do it for the test. You won't need to for the test because it'll be second nature to you by then. But let's stop at 158. Does that answer your question, Brennan?
Yes. Thank you.
Okay, I think that is right. Let's see. So V is in this direction, D is into the page, and so it's going to be to the left, or the negative X. So E is right. It's a little better. The right-hand rule seems a little goofy, right? Holding up your hand and doing that stuff, but it really helps you to think about the three dimensions that are going on here with the right-hand rule. So don't be embarrassed to try it. What is the direction of the magnetic force here? Remember, you can eliminate some, and y'all are doing much better, by the way. But you can eliminate some. Notice that I have X and Z already taken up, so it has to be either up or down. All right, so I'm going to stop at 55. 55. Okay, good. D is right. All right, so here I have V is in this direction. My magnetic field is into the page, and so my thumb points up. That was D, right? Was that D? Yeah, D. So upwards is the right direction. All right? Let's see. What word, this is not a joke, it's just sort of a riddle. What word actually becomes shorter when you add two words to it, two letters to it? Never thought about this, have you?
What is it?
Short. Thank you. I know you wanted to say it, didn't you?
Yeah.
I appreciate you, Brennan.
I secretly do, but I just never.
Every day when we leave this class.
He's like, I heard that one. Yeah. Okay, let's do this one too. It's for a little more practice. Notice too, by the way, we'll add this little pink later, but these are all for positive charges. If you have a negative charge, you just switch the answer to the opposite direction. For negative charges, everything happens opposite. All right, let's stop at 40. 40. Okay, good, right. So V is up, B is to the right. So the force on this particle is into the face. So this particle would start out going up, and it would curve inwards like that. What's my magnetic force? Give me just a second. Hang on. Oh. All right, here it enters a uniform magnetic field. There is no magnetic field. Right. So what is the force here? What's the direction of the magnetic force? All right, so let's stop at 30. 30. All right, awesome. Is that joke worthy? I mean, that was an obvious question, right? Does that need a joke? All right. That's not a joke. It's really just a really personal question that I have for you. Feel free to answer or not. Don't answer. Don't answer. It's really a joke, okay? You ever had a bladder infection? You're in trouble. You did it. Okay, a beam of atoms enters a magnetic field region. What path will the atoms follow? We'll get into this more after this next exam, but this is like a mass spectrometer. If you send a beam of atoms to a magnetic field region, what path will they follow? All right, let's stop at 50. Okay, these are the true chemists, the ones that recognize an atom from an ion, right? Because atoms have neutral charge. Now, I don't want to differentiate. Everybody here is a chemist, or geomatics, or biology. So, but atoms have no charge, right? They're neutral in charge, and if Q is 0, then there is no magnetic force. Okay. Now, this brings up some interesting points, and we'll get to this later. Don't worry too much about it for this exam. But in a mass spectrometer, you send some charged particles through a magnetic field. You actually accelerate them with an electric field up to a certain speed, and then you send them through the magnetic field so that you have a beam of particles traveling at a known speed, that's v, traveling through a known magnetic field, that's B, and then you measure the circular path, because the magnetic force acts as a centripetal force, and a centripetal force causes objects to travel in a circular path. So if you measure their radius, then you can say something about the force that's acting. And so if I send a beam of atoms, they're going to feel no force at all. So you would say, well, gosh, the charge of those things is 0. But if you send a beam of charged particles, they'll follow one of these paths. Actually, remember, centripetal force causes circular motion. This is not a circular motion, right? This is a straight line path. Likewise, number 4 isn't a circular path, but number 3 is a circular path. So would the particles that follow path number 3, would they be positive or would they be negative? And let's do that as a clicker question as well. What I'm asking is, you send some particles through, and I want to know if they follow path 3, are they positive particles or are they negative particles? And the way you're going to approach this is you'll ask, well, if they're positive particles and they go through this magnetic field, will they feel a force that pulls them down? If not, if they feel a force that pulls them up, then that would be a negative particle. And a negative particle would feel a force that's opposite the positive particle. All right, let's stop at 40. Okay, it will be a negative particle. Let me show you why. Because if I think about a beam of positive particles, whenever they happen to be, V is in this direction, B is into the page. Positive particles would follow a path with a centripetal force that pulls them up. So positive particles would feel a force upwards. But the particles that follow path number 3 feel a downward force. And so if I have negative particles, they feel a force that is opposite the direction that positive particles feel. So negative particles would follow path number 3. Let's look at a few more. For this, you can see some combinations of this where I don't give you just V and B. Instead, I give you some combination of these. Like here, for example, I give you either F or V or F and B. So in these, we want to know, I'll do this first one for you, and then you can do the second. I want to know what is the direction of the magnetic field that causes this force. So I look at my fingers, and I have V, I have B, and I have F on this right-handed coordinate system. So I have V right here, but then I have to orient my coordinate system so that F is pointing out of the page, like this, because that's how it's listed there. And so that tells me that my magnetic field has to be to the left. I know it has to be either plus X or minus X because the other two particles take up the Y and Z axes, but my magnetic field here has to be to the left. That is the negative X or the negative I direction. How about this other one? First of all, I ask myself, is it X, Y, or Z? The magnetic field that causes this force? X, Y, or Z? Well, I have force on the x-axis. I have V on the z-axis, so it's y. So it's going to be either plus or minus y. So A is either plus y or B is minus y. Which is it? This is for the magnetic field vector. Is it the magnetic field, or your middle finger, is it the plus y or the minus y? Do people still use the middle finger as a vulgar sign? Really?
I don't think so.
It's
I
actually
don't think.
a thing to do now.
Is it a thing? Not in here.
Well, no, like, the thugs, you know.
Oh, thugs. That's
Street.
I it's just like that. I guess.
Brad Orman taught me what the middle finger meant in 4th grade. But he told me the wrong meaning of it. And so now I think it means something else than actually what I think the real meaning is.
What are you studying?
Oh, yeah, anyway, I mean, it wasn't great either. I can't say. Go to somewhere, right? So. 4th graders, man. No, it's not even 4th graders, 2nd grade. 2nd graders, they don't know anything about vulgarity. All right, looking good. Let's stop at 125. Just a few more seconds. 25. I think that is right. Let's see. So V is into the page. F. So my index finger is into the page. F, my thumb is there, and so B is in the negative y direction. You have this right-handed coordinate system. You just have to get it oriented so that your 2 fingers go in the right direction of the right vectors, like this. And so it goes in the negative y direction. All right, y'all try this other one. Notice here I'm not looking for B. I'm looking now for V. Is it A or is it B? Well, let's see. I got Z right here, and I got Y right here. So that means it has to be either plus or minus X. Which is it? B is your middle finger. V is your index, your pointer, yes. You can rotate your page around. Like if it helps you, you can sort of rotate your page around. We'll be done with this soon. Hey, John.
No, this is that.
No, if you're doing the right hand rule, make sure you get up on it. Everything else, that's fine. All right, let's stop at 52. 52. All right, so here, what are we doing here? So B is out of the page, like this. That's my middle finger. F, like this. And so it points in that direction, right? Which is what? Plus X, is that right?
Yeah.
Did I mark it correct? Yeah. All right, what do you call a dinosaur with a really good vocabulary? A thesaurus. You heard that one before? Awesome. All right, let's try this one. Just a couple more of these. And we'll do a cross product. Remember, with a negative charge, you just do the normal thing and then you take the opposite of it. All right, let's stop at let's have a 103. 103. Okay, B is right. Right. I'm glad that we only have plus X or minus X. That's great. So B is up. B is out of the page, and that tells us to the right, right? Is that B? Oh, wait, no, because it's a negative particle, so we take the opposite. So we get with the right-hand rule the right, but then we say, oh, this is a negative particle. So if you come to a multiple choice question and it says negative particle or a free response, make sure you circle that negative. I'll try to make it obvious, like here I bolded it and italicize it and all that jazz. But just circle it just so that you remember when you get to the end of the problem that you need to take the opposite of what you found. Let's see, I think this might be our last right-hand rule. What is the direction of the charged particle that it feels? All right, let's stop at 43. 43. Okay, good. C is right. V is to the right. My magnetic field is down, so the force is into the page. So C. It is a positively charged particle, so we just follow the right-hand rule. So C is the right answer. All right, index finger in this direction, middle finger in this direction, and then our thumb gives the force. Make sure you're using your right hand. Listen, if you go onto the internet and look for different ways to do this, be careful because sometimes people will teach the left-hand rule, and there are ways to use the left-hand rule. It's just your fingers are assigned differently. Or sometimes they'll teach the right-hand rule, but with different sort of nuances about it. So just be careful if you go on the internet. There are some homework problems, and I think that they're probably sufficient to give you practice, but also look at some of the old tests because you'll see some of those in the multiple choice as well. You'll certainly see some right-hand rule stuff on the test, probably 2 or 3 multiple choice, and then also when you're doing the cross products, you have to know how to do the right-hand rule to know IJK, JI negative K, that kind of business. Some of you might have just memorized that, and that's okay, but it's easier if you just know the right-hand rule. You need to know it anyway for this business. Okay? I went to give blood the other day, and they told me that I had type A blood. I don't have type A blood. It's typo. Okay, let's try this one, and then we'll do another cross product. That'll be similar to what we'll do on the test. Okay, more have it right than wrong, but ask your neighbor what they put. Yeah, she gets the tricky ones, doesn't she?
She's sharp.
She is very smart, Frankie. Is that your given name, or is it short for something, Frankie?
We have a bunch of nicknames for
All right, let's stop at 57. 57. Okay, yeah, so we were sort of spread out all over the board, but A is the right answer. Why is A the right answer? Why is there zero force?
the same direction.
Right, it's a very key word here that the electron moves in the same direction. So my velocity vector is in this direction, and my magnetic field is also in that direction, so it feels no force. Remember, F was QVB sine theta. And so since theta here is equal to 0 degrees, the sine of 0 degrees is 0. Likewise, the sine of 180 degrees is also 0. As you know, it's that x-axis. All right, let's do this. Probably have one that's similar to this. We have a couple actually we'll run through. So we want to do our cross product. Our force is QV cross B. I'm going to do this one, and then I'll let you do the next one. Our charge here is a proton, so that's 1.6 times 10 to the minus 19 coulombs, and it's moving with a velocity of 2I plus 1J. Remember, the order in cross products is important because I cross j is equal to the negative of j cross I. So if you get your v and your b mixed up, then you'll get an answer that's the wrong sign. 2i plus 1j, and then b crossed is 1i minus 3j. Then I do FOIL. But as you know, when we're going through our cross products, we know that I cross I and j cross j, those are both equal to 0. So I can just leave out this one and this one. Both of these are equal to 0 because I'm taking the cross product of two parallel vectors. In this case, parallel and in the same direction. So I'll just do a couple of these. I'll do 2i and negative 3j. That's my, what is that? What is that in the FOIL? First, outer, inner, last. Anyway, it doesn't matter. And then I'll do these two as well. So I have 1.6 times 10 to the minus 19 times 2 times negative 3, that's negative 6, I cross j, plus 1 times 1, that's 1, times j cross I. You probably remember that I cross j is k, but if you forget, just draw your coordinate system up here. Have I, j, k, those are my x, y, z axes. Right-hand rule, just like we did before. I, j, thumb gives the result of that cross product, which is in the positive k direction. And then you probably know that j cross I is the opposite of I cross j, but if you forget, j, I, thumb goes into the page for j cross I. So I have I cross j as k. And j cross I is negative k. So my answer then is negative 7 times 1.6. What's that? 70 plus 42. 11.2 times 10 to the minus 19 newtons in the k direction. In the negative k direction, so negative 11.2. All I did was multiply 7 times 1.6. Isn't that right? 70 plus 40. Yeah, 112. So 11.2 times 10 to the minus 19 newtons in the negative k direction. All right? So you'll have a free response that'll be like this one, or maybe like another one that we'll do. We'll see. Yeah, I'll try this one out, okay? What is the force here on this vector, on this charged particle? I'm going to start writing down our known values up here. You can keep working. All right, normally our FOIL has 4 terms, but I'm going to take out one of those terms because I know that these two, j cross j, will be 0, so I'm just going to leave out the last, or excuse me, what is that? That's outer. So I'll just leave out the O, so instead of FOIL, it's just going to be, you know, fill or whatever. So we do the first. That's 2j and 6i, so it's negative 10 times 12j cross I, and then I do 3k and 6i, it's my inner, that's going to be plus 18k cross I, and then I do the last, which is 3 and 8, that's 24 k cross j. All right, being careful to make sure that I get the order of the vectors correct. And now doing those all together, I find that's equal to negative 10. I like to draw my coordinate system, I, j, k over here. And then I ask myself, what are these? Well, j cross I we've already done, that's negative k. But if you forget, you know, j, I is in that direction into the page. Now the k cross I, k is out of the page, I is to the right. So k cross I is in the j direction, the positive j direction. And then k cross j, k, j is in the negative I direction. So my k cross j is in the negative I. So it's going to be 10 times 12, negative 12 rather, because the k is negative, plus 18j minus 24i. And then we just take the 10 through. Remember, this was a negative 10 Coulomb particle, so it switches the direction of all those vectors. So it's 120k minus 180j plus 240i. All right? So you'll have a problem that will look very similar to that. I think, in fact, that we'll just, well, we're not going to stop right now, but we'll cut off the test at this point. Yeah, y'all prefer to cut off the test at this point, wouldn't you? Okay, that's fine. The next problem is basically identical to this. There's just one little added complication, but we'll save that for the next test. In fact, we probably won't even have it for the next test. We'll probably just sort of gloss over it. But as far as the test is concerned, we'll stop right there. I do want to show you, geomatics folks have probably done vectors in 3D. Is that right? Do vectors in 3 dimensions? All right, so we treat them a little bit differently than we do in vectors in 2 dimensions. Now, you're not going to have to find the magnitude and direction of these vectors, but I just want to sort of point this out to you. If I wanted to know, let's see, this is my force. If I wanted to know the magnitude and the direction of the force, I would say the square root, normally it would be the square root of the x squared and y squared components. I'd do the square root of 120 squared plus negative 180 squared plus 240 squared. And then that would give me the magnitude of that vector. So in 3 dimensions, when I have vectors with x, y, and z components, if I want to know their magnitude, you still use the Pythagorean theorem. You just add a third term. So the Pythagorean theorem looks a lot the same as it does in 2 dimensions. But instead of just having x and y, that you also add in that z component. It works exactly the same. But when you're doing the angles, you actually have 2 angles that you have, 2 or even 3 angles, right? There are 3 angles that you have to, or just 2? 3? 3? I don't usually do this, but so like for example, let's say that you have a vector that's off here in both all 3 I, j, and k directions. You have to define all these different angles in order to define the position of that vector. And y'all can do it, like you have the ability to do it. It's just trigonometry like we've been doing, but we're not going to have to do that for the class. And I don't know, some of you chemistry majors might get into this later down the road where you have to do 3D vectors, but probably not. You geomatics guys, y'all have to do that quite a bit, right? 3D vectors. So, but not for this test. You'll just have to give the force in IJK notation, in vector notation. Listen, this should be an easy 7 to 10 points on the test. I want everybody to get it exactly right. Numbers will be easy. I might give you a proton or electron, so you have to do that 1.6, so that's 19. But just make sure that you know how to do your cross product. Knowing your right-hand rule will help a lot with that, helping with your IJK notation. But I want it to be an easy, I want to just fly through them and say, gosh, these are all perfect, and do minus zeros on all of them. Okie dokie? What time we got? 8:20. All right, so that is the end of the exam, and I think we'll just call it off here. Now on Wednesday, we're going to do review only. We got a lot of stuff on this exam. Those multi-loop circuits and those combination circuits, those are going to be tough for y'all, so make sure that you're good on that. Be practicing those in the next couple of days. Also look at your RC circuits. Make sure you know your household circuits. Make sure you know current, power, all those definitions, and make sure you're good on the cross product, okay? All right, I will see you.